Today we're going to be continuing our discussion of number systems with hexadecimal. Which is base 16. As such, it has 16 symbols. When you run out of the normal decimal symbols, you start using letters. So it's 0 through 9, then A, B, C, D, E, and F. These correspond, of course, to the decimal values. 0 through 15. Okay, so that's hex, decimal, one of the nice things about hexadecimal is it converts to binary very easily. So the binary representations of the hex number, hex digits, a single hex digit represents a nibble, or 4 bits. And it is all the combinations of 4 bits. That are possible. So to do the conversion from hex to binary, you just substitute the hexadecimal digit with the corresponding binary, 4 binary digits, 4 bits. Now like binary and decimal, the digits correspond to the powers of 16. I don't expect you to remember the powers of 16 too extensively, but 16 to the 0 is 1, the 1's position. 16 to the 1 is 16's position. 16 squared, to the second power, is the 256's position. 256's position, and the 16 to the third power is the 4096's position. As you can imagine, you can represent very large numbers with fewer digits in hexadecimal than you can with decimal or binary. So, given this, you have 1, 3, A, C, for example, in base 16. Converting it to decimal, you multiply the value of the digit by the value of the position. So it's 4096. Let's see here. 3 times 256 is 768. A, it corresponds to the decimal value 10, so it's 10 times 16 is 160. And C corresponds to 12, so 12 times 1 is 12. Now, if somebody has a calculator, they can add this up for me. 4096 plus 768 plus 160 plus 12. You already got that handy? I'm sorry? 5036? In base 10. So you multiply the value of the digit times the value of the position, and then you add up the totals, just like you would in binary. It's just you got to remember what the A, B, C, D, E, and F represent as far as decimal values. So you get quite large numbers quite quickly. Hexadecimal is often used for addressing. A 64-bit computer has a 64-bit addressing scheme. It can address values from 0 to 64 zeros to 64 ones. I think that's in the exabyte area. Trillion or quadrillions of possible addresses. But 64 bits, it would be a string of 64 ones and zeros. With hexadecimal, because each digit is represents 4 bits, 64 bits can be represented with 16 hexadecimal digits. So memory addresses are typically represented in hexadecimal. Now converting to decimal to hexadecimal, let's look at the 1, 16, 256, and 40, 96. And let's say you're converting the number 7,842. All right. So how many times does 4096 go into 7842? Just one time. So it would be one in that position, and deduct 4096. And then how many times does 256 go into 3746? Anybody got a calculator handy? Don't need the decimal, just the whole integer math. 14? 14 is E, so E, and what is 14 times 256? $3,584? 3,584. Deduct that from the total, the running total here. You get 2, 6, 1, 162 left over. And 16 goes into 162 10 times. So that's A, because 10 is A. And then you deduct that. Leaves 2 ones. So your result is 1EA2. And yeah. Yes. Base 16 is hexadecimal, yeah. Yeah. Now to convert that number to binary, just as a exercise, 1 is 0001. E is 1110. A is 1010. And 2 is 0010. See the groups of 4, each nibble corresponds directly to the hexadecimal digits. So it's good to, when you're doing conversions and have to go between hexadecimal and binary, it's good to write this out until you've committed it to memory. The conversions between hex and binary. So and then you do the same technique for negative numbers as you do for binary. You would, let's say, take a negative base 10 number, let's say negative 47. You would convert the 47 to binary. So that would be a 32. That's 15. And so, oh, well. One, two, oh, there's a 0 in there. So 1, 0, 1, 1, 1. So that's equals 47. And then you would invert, but first you need to pad with leading zeros to make it an even number of nibbles. So add 2 zeros because you have 6 digits here, 6 bits. Then you invert 1, 1, 0, 1, 0, 0, 0, 0. And then add 1. Then convert it to hexadecimal because you have an even number of 4 groups. So 1101 is D, and 0001 is 1. So negative 47 base 10 is D1 in base 16. No negative sign. It is just understood that the leading 1 is going to be an indicator that it is a negative number. So to do negative numbers in hexadecimal, you have to convert to binary first, and then do the simple substitution between binary to hexadecimal. As a little indicator of what might be a negative number is if your most significant digit of your hexadecimal number is 8 or greater, then the leading zero or the leading bit is going to be a 1, making it a negative number if it is a signed number. If it's unsigned, just it's calculated as normal without doing the 2's complement. But if the say CA 1, 5, and 16, C has a leading 1, so this would be a negative number in base 10. Whereas 6, 4, B3 has a leading 0, so it would not be a negative number. Just a quick trick to see if you got the right result going on. Let's see here. Doing math with hexadecimal, I wouldn't even bother trying. It's, what is B times C, D? You could theoretically use the shift and add method of multiplication. So you would do, say, 4C times 1B. What's B times C? Huh? What's that in hexadecimal? Exactly. It's not it's not a easy problem to attack from this angle. So it would be much easier to convert it to 0, 1, 0, 0 and 1, 1, 0, 0 and 0, 0, 0, 1. B is 1, 0, 1, 1. And then do the math that way, the shift and add method that way. So it would be 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0. Bunch of zeros here. Am I missing something here? No, no. And then 1, 0, 0, 1, 1, 0, 0, 1. And then another time. And then add up is 0, 0, 1, 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. And 1, 1, 1, and 1 is 4, which would be 0, carry the 0 and the 1. So 0, 1 and 1 is 2, which is 1, 0, carry the 1. 1 and 1 is 2. 1 and 1 is 2. Huh. Lots of zeros. Anyway, and then you would convert that back to hexadecimal, which would be 8, 0, 4. So the end result is 804 in base 16. Follow that? Kind of, sort of? No? Okay. So for C converted to binary, and then 1B converted to binary. Okay. And then you just do the shift and add method of normal math, where you have if there's a 1, copy the whole number down here. If there's a 0, and shift and do it again for the second digit. For the third digit, it's zeros. So you just put zeros as a placeholder there. 1 times that is that number again, copied down here, and 1 copied down here, and then you just add them together. Then convert them back to hexadecimal. So, I mean, it's this. It is the same process of math. You know, the shift and add method of math that you've been using since 3rd or 4th grade, just with ones and zeros instead. So, you just, for doing the math, adding or multiplying, you would convert to binary first, do the math, and then convert back to hexadecimal. Because the conversion from hexadecimal to binary and back is easier than figuring out what B times C is and in hexadecimal and what do you carry over here, and it's just a mess. So rather than learn a whole different system of a whole different multiplication tables, you would just convert to binary and go from there, because the multiplication table for binary is a lot easier. Which we'll get into next week with the logic gates. We'll see how multiplication is done in circuitry. Kind of. We'll get in more detail later, but now for addition, you can do say it's 4C plus 1B. B plus C is 23, which is what in hexadecimal? 17? So it'd be 7, carry the 1, 67. So doing addition in base 16 is a little bit easier. Subtraction, I would suggest doing the 2's convert to binary, convert the second number into a negative number in binary using 2's complement, doing the addition of the binary to the negative number, and then taking the result and converting that back to hexadecimal. A little bit longer way of doing it, but let's say we're doing 4C minus 1B. C minus B is 1. Okay, it's easy. There's no borrowing involved, but with the potential of borrowing, say this was say this was F, 1F. F is greater than C, so you have to borrow 1 from this column, just like in regular subtraction that you would do in middle school or in elementary school. So 1C is 16 plus 12, which is 36, right? 16 plus 12? No, 16 plus 12 is 28. 28, sorry. So yeah, I'm saying gets a little confusing. 1C is 28 in is in decimal, minus F, which is 15. So it would be 13, which is D, and you would have 2D as your result. Just as a curiosity, does anybody in here have a non-Texas Instrument a scientific calculator? Nobody? Oh, what kind of? Check the Casio. Pull out the Casio for a second. Is it scientific? Is it a scientific calculator? Let's see here. Yeah. Let me see if I can.
Those are like all the modes, I guess.
Yeah. Let's see here. Check to see. Check the manual and see if most Casio scientific calculators have number conversions on them. Texas Instrument do not.
Oh, the base equals.
Yeah. Put in the base and go to base. Let's say base 16, and check my math on those. You'd have to do shift and then the letter to enter in the letters in the on the keypad.
Wait, how do I change the base? It says decimal right now.
Oh, okay.
Format. Okay, now it's in hexadecimal.
There you go. There are some scientific calculator apps on phones that also have number conversions on them, functions in them as well. But this is why I asked you to show your work, so you can do it by hand. And if you have the capability to do it on a calculator, such as he can, you can check your work to see if you're accurate in your conversions and math. Okay. All right. But like I said, Texas's Instruments calculators. I have yet to see one that has number conversions on it, so I don't know why. Scientific and engineering calculators should have binary, hexadecimal, and as well as decimal number systems available to the user. But any questions on hexadecimal? I mean, it's just another number system. Same rules apply. as a this isn't really important for this class, but when you get to other classes that use binary and hexadecimal, let's say you have 101. What base is it? It could be base 10, it could be base 16. I'm sorry? Well, when you type it into a computer, if you just type in that, it's base 10. If you want it to be binary, you would precede it with a 0B. Because you can't do the subscripts like you can do on paper and like what I've been doing here. So if you have a binary, if you want to represent a number in binary, which sometimes you do want to do that sort of thing, precede it by a 0B, and then your string of ones and zeros. If you want to do hexadecimal, you would precede it by a 0H or a 0X. I personally prefer the 0X. I don't know why, just a personal preference. But so if you can write this notate them this way on a test or a quiz or homework if you want. You could use subscripts if you choose. Just make it clear what the number is, what base number the number uses, because 101 in decimal is significantly different than 5 in binary, which is significantly different than, what is that, 257 in hexadecimal. So any math or addressing or what have you that you're going to be using, it will be significantly altered and or affected by your designation of what base you are using to represent the number. But let's see here. Anything else about hexadecimal that you might need to know? Let's see here. Hexadecimal is a fairly easy once you get past the learning the 6 extra digits of the number system. It's a fairly simple number system to use. I'll go ahead and share with you. You can use any number greater than 2 or greater than 1, or so 2 or greater for number systems. Any number greater than 1 can be a base. So you can have base 7 with 7 symbols, 0 through 6. In older systems, older computer systems, you'll run into what's called octal, which is base 8. And it goes and the octal digits correspond to binary groups of 3 in binary. So octal is not used very frequently anymore. Hexadecimal has basically replaced its use, but some legacy systems from the 60s and 70s, which are still around and people still do use and maintain, will use octal. Some scientific calculators even have octal number conversions on them. But same rules apply. For math, I would suggest doing the convert to binary, do the math, and convert back because of the simple substitution. Negative numbers, again, convert to binary. Do the 2's complement and then convert back, convert with a simple substitution with this little substitution chart here. So it is not likely you will run into octal in your careers, but it is possible. Let's see here. Well, I guess that'll be about it for the day, unless there's any questions or if you want any more examples to be done. Yes.
So on the homework, you said how like the 0B is binary. So on
Yeah.
degree, like when you have that 0B, for example, when you had the 0B 101 101, is the 101 in binary, or is that in base 10 and you're just using the 0B?
0B indicates the following number is in binary.
Okay, so that would have base 2.
Yeah, or I didn't want to go through the process of putting a subscript on all those numbers in Microsoft Word. It's just kind of a pain in the butt. So I use
Same thing as a like a subscript on it.
Yeah, of base 2, of 2, yeah. Yes.
I just want to like if we could do an example from now, like not the actual time.
Okay. What do you have one in mind?
No 7 convert 0B 1110.
From binary to hexadecimal? Okay. Well, how many digits was that? 7 digits? Okay. So let's say we have, I'm going to just choose a random number, 101101. Okay. to convert that to hexadecimal, you need groups of 4, groups of full nibbles. So this is 7 digits, so you have to add a leading 0. So you would group the 4s together, each group of 4 together. 101 over here is 5, and 1101 is 13, which is D. So you would have 5D.
Yes.
That's it. It's not, really complicated stuff. I mean, it's just ones and zeros. Yeah, I tell people, people ask me what I do, and I tell them I teach at Jackson State, and they ask me what I teach, and I say, oh, the easy stuff, computer science. And they're like, easy stuff? It's just ones and zeros. That's all it is. That's all a computer understands is ones and zeros. I make the analogy to a brick. A brick is a very simple, straightforward, can't get much easier shape, right? Yeah, look what architects have been doing with bricks for thousands of years. Designing these elaborate, complicated buildings. Same thing with computers. It's all ones and zeros. Can't get much simpler than that. So, don't overthink it, and look past the complicated presentation of what you see on your computer screen every day, and see the simplicity of it. When you get into assembly programming, quick show of hands. Who here is computer science major? Okay. Everybody else is going to take computer org, where you learn assembly language, and the entire language has 136 words in it, or 124 words in it. That's it. Very simple. The English language has like 600,000 words in it, most of which we don't use or aren't even familiar with. But what we use on a daily basis is in the tens of thousands of words. The assembly code is a direct translation of what the machine can actually execute. And that is, in the case of the processor that we study in computer org, 124 different different things. And that's it. All the things you could do with a computer, you can do with those 124 different commands. So it is, people say that this is a complicated topic or field of study. It's as complicated as you make it. I see it as fairly simple. Not because I'm some sort of genius or anything like that. It's just I've seen past the complicated presentation to the simplicity behind the scenes. I ask you to do the same thing. When you see a complicated, see something on your computer, what goes into that? What's the logic behind that? That sort of thing. And that's what you're here to learn about. Starts with digital logic and basic programming, like in Computer Science 1 and 2. But Yeah, it's C++, the language of computer science 1 and 2, has a vocabulary in the language of on the order of like 30 some odd words, and that's it. Everything else is user defined or library defined. But those libraries use those 30 some odd words, and you just make modules and snippets of code here, snippets of code there. Pretty soon you have a big complicated application. But when you get right down to it, it is simple stuff. You want complicated? Go to the math department. That stuff it gets complicated. Talking about just differential equations and linear algebra and all that fun stuff. That's the complicated stuff. I'm not that good at that stuff. This stuff I can understand, but Cal 4, way over my head. Anyway, that's my spiel on the simplicity of computers. Anyway, there is going to be a quiz on Thursday on number systems. Very similar on in problems as the homework. Different numbers, of course, but it is open note. It is you can use a calculator, although you would need to show your work on some. You'll need to show your work on some problems to demonstrate that you understand the process. In the meantime, have a good day.